Hi, everyone. So let's start the class. So turn on video. Hi. Sure. Okay, so we start. So today we first want to have the breakout rooms for exercise 5. So we continue that for maybe the first 15 minutes, and then I explain the solutions. Exercise 5, the problem 1 only. And after that, I'm thinking to skip the graphs and figures in chapter 4, and we go to chapter 5. And chapter 5 is the statistical testing. So we have the more statistical materials rather than R. So chapter 1 to 4 are more R coding, and chapter 5 and later we have both statistical theory and R coding. Okay, so let me share the screen and review the exercise 5 questions first. So this is exercise 5. So at first, you can download the Apple dataset, and this includes just the observations. So first column is date, and the second column is the Apple stock price. So you can see this is the dataset. So just we are using this price, the second column. But this is price itself. So we want to see the return of the Apple stock. For example, from October 1st to the October 4th, that we have, I don't know, the 53 cents loss in price. That is about 1.5%. And we want to formulate this as log of this number minus log of the previous number. So basically, we want to do this. Sorry, the 53 cents. So log of this. I think that this is different from R. So maybe we have to use ln or something. Oh no, log 10. Only negative 0.6%. 53 cents. So it's more than 1%, but the log of so Excel is not really our, yeah, I think that this is log 10. So I think that we have to use the natural logarithm, but basically we have to take the log of this number minus the log of this number. This is approximate value of the return. So you can see that I think this includes some answers for another course. So, okay. Yeah, you can type the log of, for example, 37.83 minus log of 38.39. Sorry, this is the 86. So yeah, you can get the negative 1.4% approximately. So we transform this, that is at first that we have to do. Then after that we standardize it. So we subtract mean and standard deviation. So this YT tilde is the vector we want to use. And we want to use, we want to make a histogram first in B, and we want to make several QQ plots. So one is the QQ plot with T2 distribution, then T3, T4, T5, T6, and normal distribution. So you have to calculate the theoretical quantiles for these distributions, and also actual quantiles are this one, the YT tilde. So we have to compare the theoretical quantile with actual by using plot. And see all 6 plots and see which one that follows the most, straight line. Okay, so do you have any questions so far? If not, I will set up the breakout rooms. We have the 18 students here. So maybe I set up 4 rooms. I will check the attendance as well during the session. So maybe at least 15 minutes. Okay.
I think it just sent me back to the main group.
You cannot enter the room?
I was for like 2 seconds and it just sent me back here.
Oh, okay. So you have to, maybe I have to put it in your some group, right? So Neil isn't any, okay. Sorry, you can join the room too, right?
It put me there. How do I join it?
I think the somewhere
Yeah, I've never
of
had
the
this happen before.
button, I don't know if it's possible to force
Okay.
you to the room.
Oh, here,
Hello.
I found it. Okay.
Oh, you find it? Okay,
Yeah, thank you.
good, good. Sure. Okay, I think everyone came back to this room. Yeah, okay. So let's start. I think the one room at least finished all QQ plots. The conclusion is different from mine, but I think the one room concluded T5 fits the best. Any other room finished the all QQ plots and decided which one is the best? No, we haven't finished. Anyone? No. Okay, then maybe I will share the screen and do the job. Yes, the coding is try and error process. So maybe sometimes it's better to show our screen, even if it's redundant. Okay, so we have to set the working directly. So usually it's the good way is at first we get the default working directly, and then okay, so you get the exact path. So WSUSD. Okay, so this is exercise 5. Okay, then we have to read the table Apple APL. I don't know APL.
Double A.
Yeah. So originally there is another company called APPL something. So that ticker code was reserved for that very small company in Texas with 2 employees. But now I think anyway, so that's why this file is named AAPL, not APPL. Anyway, so we define this as the data set, D. You can check the data set. Once you created something, it's good to check the content. And okay, so we have the 1007 observation. Oh yeah, so we have to read this as, okay, maybe head to D. Yeah, actually it cannot read the data in the correct format. So we have to specify the separation symbol is comma, and also we have header in this one. So then head of D, yeah, this one. Okay, so now we want to take the log of price. So at first the D of price that we define this as maybe X. Then the X is, so this vector with 1007 observations. Then we have to take difference of X, so that this is Y. So Y is a vector with 1005 observations. Sorry, the X include 1006 observations. So we have 1005 differences. So this is Y. Okay, so now we want to standardize this. So we have to, not difference. So we have to define Y as log of X minus the log of X minus 1. So to do that, I think one good way is we extract second to 1006 observation, and we subtract this from subtract the log of X of 1 to 1005. In this way, we can calculate log of X2 minus X1, X3 minus X2, X4 minus X3 at the same time. So then this is Y. So histogram-wise, what? The histogram of Y looks like this. But we want to standardize it because we want to compare it with standard normal random variables and also the t distributions, which are almost standardized. So yeah, So we want to standardize it. So y minus, so y tilde, maybe we say yt, y minus mean of y divided by standard deviation of y. Then we can make a histogram of yt. Y tilde is this. It looks like almost normal distribution. Yeah, but so we have created y sub t. This is the answer for A. And B is the histogram, but we want to make actually this is the histogram with increment -2, 1, -1, 0, 1, 2, and so on. So yeah, so this is the histogram for B. So now we want to compare this with theoretical quantiles of t distribution and also normal distribution. So for number C, that we have to create the theoretical quantiles. Or maybe T2 first. So that can be done by Qt. Qt is the F inverse function basically in the slide. So F inverse. F is basically probability function, and the Qt is inverse of probability function. And we have 1005 observations. So we have to put this 1 over 1006, 2 over 1006, and so on for this. Up to 1005 over 1006, right? So remember that in the slide, we have 4 observations. So this is just for explanation purposes. 4 observations, and we calculate F inverse of 1/5, 2/5, 3/5, and 4/5. Here we have 1005 observations. So we have to calculate F inverse of 1 over 1006, 2 over 1006, up to 1005 over 106. So we have to put this. So 1 to 1005 divided by 1006, and degrees of freedom is equal to 2. I think this should be lowercase. Or T2. So, sorry, maybe I have to name it in some way. It's a nightmare. So we have to name this as theoretical quantile for T2. So maybe we name it as Q2, maybe Q2. And this has 1005 observations, you can see. And now we want to create QQ plot. So sample quantiles are Y sub t, and theoretical quantiles are Q2. So basically, we have to do this, the QQ plot for T2. Yeah, and actually this isn't really the answer, but this makes this graph. So x-axis is theoretical and y-axis is empirical, but we cannot really see any curve pattern because this y sub t is not ordered. So remember that when we use the QQ plot, we make a QQ plot that we have to align observations by increasing order, then compare it with this Q2. So we have to sort this. And this is the answer, okay? And we can obviously see that we have the S-shaped pattern. So it's not really on the straight line. Maybe it's not super terrible, but at least it's not ideal. So Q2 is a little off. Then we have to do this for Q3, Q4, Q5, and Q6 in the same way. And also that we have to do this for normal distribution. For normal distribution, maybe we write Qn. So this is obtained by Q norm function and no degrees of freedom. This is for normal. Then we can do it in this way. This is for normal. And the normal, actually, this is a kind of inverse S-shaped. So sample quantiles have more outliers compared to theoretical quantiles. So T2 distribution is very heavy-tailed distribution. We have many outliers, and actually those outliers are more than empirical the outliers, so actual outliers. But here, actually, the theoretical distribution doesn't have many outliers, so sample quantile is the more extreme. Theoretical quantile is just -3, but theoretical realization is -3, but the actual number is actually -8, so much more outliers than normal distribution. Now I think I can share all the results. I think we can use some function to show it at once, but we can just to save some time that we want to show this. What's this? Yeah, so this is the figure. And these 6 figures, okay. And yeah, actually the one breakout room, concluded this one. Yeah, this one is almost close to D5, but my best choice is maybe T3, possibly T4, because when we see outliers, the T4 follows the most straight line, and T3 follows the most straight line. T4, actually at the center, maybe it's even better. So maybe this is also the possible answer, but we have some outliers here. So this observation is off the trend line compared to this. So I would say maybe D3, maybe D4 is also fine. D5, clearly this observation is too small. So the benefit of thinking about QQ plot is, we can see the upper tail and lower tail very well. So if we just watch this and this part, probably I would say T3 or maybe T4 fits well. The T2 and the normal, that obviously looks bad, and also T6, maybe it's almost a similar shape as normal. So I would say T3 and T4 are the best fit for this. And generally, normal distribution isn't the best distribution to fit the stock market return, and often T4 or T5. Yeah, T3 is pretty heavy-tailed, but this is individual stock. So if we do stock index, usually the T4 or T5 is chosen. Yeah, I got some message. Yeah, I'm going. Yeah, sure. Mm-hmm.
I have a question.
Yeah, sure.
Could we like objectively measure the like how off it is by taking the square difference between the theoretical and the
usually we don't do that because these outliers are important in several reasons. For example, stock market return, that we have to predict the worst case scenario or something like that. So 1% worst case scenario or 0.01% worst case scenario. So that means that we should put more weight on these extreme observations. So because of that reason, usually that we don't do that kind of metrics. Yeah. So in some sense, it's vague, but this is how statisticians established the theory. Yeah, but that's a very good question. So especially you are a logical person studying mathematics. Naturally, we want to fit the least square method or something. But for this case, no, we don't do that. Yeah, still we can do some weighting and maybe you can establish some theory. Yeah, that can be good to research a topic. Right? I haven't seen such creative research topic before, but who mentioned that? Who asked the question?
Me.
Oh, okay. So yeah, you can do that, topic for final project if you would like. Yeah. Maybe you established some method to objectively measure the QQ plot. Yeah, yeah, that's a fantastic project. Okay, so now that we go to chapter 5, do you have any questions so far? chapter 5, we have more theory. So I think rather than I share the screen, I will share the screen from iPad and handwrite something to explain this. And so just a moment, I will share the iPad screen. Yeah, so chapter 5, the 1 and 2 sample tests. So basically, I review all concepts in statistical testing. Maybe you have already studied in Stat 2210 or 1020, but I would like to explain it. So at first, recall that the hypothesis testing is a decision-making rule between the null hypothesis and alternative hypothesis. So testing is basically deciding between H0 and H1. So conclusion is either that we reject H0 to support H1 or we accept H0. So we only have two choices. And two choices are not symmetric. So H0 is rejected only when there is a strong evidence that H0 is unlikely. Otherwise, H0 is accepted. So basically, we want to support H1. So we want to have the strong evidence to reject H0. Then we can certainly say H1 is true. And H0 is, yeah, so that's the case, yeah. So H0 and H1 are not very symmetric in usual hypothesis testing. Yeah, we only have strong evidence to reject H0. We reject H0 to support H1. So here is an example to explain that situation. So suppose that we found out that the 51 out of 100 newborns are male and 49 are female. And we want to test if 50% of babies are male in the United States. Against the alternative hypothesis, not 50% of babies are male in the United States. So we have just a small sample in our data, so that we have only 100 newborns. So, this proportion, 51 over 100, is not exactly 0.5. This is 0.51, but that is close enough to 50% maybe. So in such a case, we do not reject H0. So that is the idea. So do you know if there are more male or more female among babies for human? Maybe for most animals.
Can I guess?
Yeah.
Males?
Yeah, you're right. So basically males are weaker than females. So originally we have more male. So that is probably the theory, right? Yes, so we have usually more male, like the 50.5%. Maybe it depends on country, maybe it depends on other factors, but usually 50-point-some%. So this is really interesting, hypothesis testing. But with small sample, only 51 out of 100, that isn't probably much different from 50%. So we have to set some threshold. If this number is maybe 65 over 100, maybe most people believe that this is, an evidence that we have significantly more male than female. Yeah, so yeah, that is hypothesis testing. And here is an example. So here that we establish test for continuous variable first. So the example is math PhD salary. So these figures are starting salaries for 7 math PhDs. And 45,000, 80,000, 50,000, 95,000, 65, and 110, and 48. So this is typical mass PhD salaries. If they become postdoc or some academic career they pursue, then the salaries are this range. If they go to industry and work for Meta or Apple, then salaries are higher. Maybe these days it's even higher. And suppose that we have some average salary for all PhDs, that is 79,500. And we want to see if the mass PhDs from maybe specific, maybe university has the same salary as average PhDs in the United States, or higher or lower. We want to test. And we assume that the salaries follow normal distribution. Possibly, if it's not normal, we can transform by some function to make it normal, and test whether the average starting salary for mass PhD is significantly different from 79,500. So here, the null hypothesis is in this maybe department, the mass PhD salary is 79,500, and alternative, it's not. And how to judge this? Maybe at first you can calculate the sample mean. The sample mean is, I think, 75,000 or something. So you can calculate this. And I think somewhere I have slides, but yeah. The average is actually 70,400. Approximately. So, okay, so this is lower than this one, 79,500, but it's not really sure if it's significantly lower or not. So we have to decide that when we say this is significantly different from 79,500. So this is essentially the considered deviation from this 79,500. So we want to reject H naught if X bar minus 79,500 is far away from 0. The question is, what is the far from or far away from? And one factor is, the difference. Difference is 9,100. But another factor is the variation within these observations. In a common sense, we have large variation in the sample. Even if we have some difference, we cannot say these are significantly different. But if our 7 PhD salaries are like 69,800 and 70,000 and the 70,300 and 70,400 and the 70,500 and the 70,800 and the 70,000 maybe 71,000 maybe. Then, this has very small variation. So you can certainly say that this average is significantly different from 79,500. You can see all observations are much less than 79,500. So even if, okay, so these 7 observations also have mean 70,400, but this is different from our situation. So basically, we want to see 2 information. So one is deviation. One is the difference between these 2 numbers, sample mean and our hypothesis. And another one is the standard deviation. So variation in this sample. So we want to use those 2 information to test. So that is the idea. And here is the theorem. So suppose we have observations x1 to x10, xn. And these are from independent observation. These are independent normal observations. And independent and identically distributed, the normal observations. And the suppose that the population is normal, the mu naught and the sigma square. We are interested in this true population mean of these observations. Then actually, this statistic, that is the sample mean minus this hypothetical number, in the previous example, 70,400 minus mu naught, so 79,500 in the previous page. This is 7,400. Okay. Then divided by standard deviation. Standard deviation was pretty high in 7 mass PhDs. So maybe standard deviation maybe to 20,000 or maybe even larger. Then divided by square root of n. If we have 7 mass PhDs, square root of n. Okay. So this quantity follows T distribution. T distribution, we have already studied it. So based on this property, we can see if this statistic is too large or too small. And you can see that this denominator, maybe this numerator first. The numerator is the difference between two means. And the denominator represents the variability. And also we account for the sample size. If the sample size is large, we have stronger evidence. So that should be reflected to our criterion to reject H naught. So actually, if we take the difference, we divide this difference by the size of variation, standard deviation, and we adjust for sample size, then this statistic T follows the T distribution with df n-1. So if null hypothesis is true, so if the center is mu naught, then the T follows the T sub n-1. This tilde means the left-hand side follows the distribution on the right-hand side. So T follows T distribution with df n-1. And capital T is called T statistic. Any questions so far? So the idea is to account for several informations, the difference between our hypothesis and actual mean, and the standard deviation of the sample, and also sample size. We use those three pieces of information to see if T is so T follows, so T is in the normal range. Yeah, and okay, so T represents the good information. So we reject H naught if T, absolute value of T is extremely large compared to the distribution. So this is the T distribution with df n-1. Okay. And if null hypothesis is true, so average salary from specific department, we have 7 observations, but in the long run, if the average mass PhD salary is 79,500 in that university, then T statistic follow this distribution. And if our realization of this T statistic is really extreme value, such as negative 4.5 or maybe positive 3.8, then it's very unlikely to happen. So if we assume H naught, these are very unlikely to happen. So we reject H naught. So that is the idea of statistical testing. So we think about theoretical, distribution of capital T. And if we got extreme value under this distribution, then probably our assumption, our hypothesis is incorrect. So that is the way of statistical testing. Yeah, and to be exact, usually we set the 5% range or 1% range to reject H naught. So this shadowed area, so this area is the 2.5% of entire area under the curve. And this is also 2.5% of entire area under the curve. And if our test statistic falls in this shadowed area, we reject H naught. And this shadowed area is called rejection region. So maybe less than negative 2.5 or more than 2.5. So this is rejection region. Do you have any questions so far? Okay, so yeah, this is the R code to draw the previous figure and also another figure later in slides 9. Yeah, I don't review it in detail, but this is density function. So we use the dt function with df6. Oh, here we have 7 observations. So n is equal to 7. So df is n minus 1 in the previous theorem. So this is 6. Okay, and what is our t-statistic? This is sample mean, this is standard deviation, and this is sample size n. And if you plug in these numbers, or this is the mu naught, this t becomes negative 0.94652. So in this previous distribution, negative 0. In the previous distribution, negative 0.94 is actually not really extreme value, so 0.94. So this is actually in a typical value in this distribution. So we don't have any strong evidence to reject H naught. Yeah, so that is the conclusion. And to be exact, what's the threshold value to reject H naught? So that is, okay, so lower 2.5 percentile and upper 2.5 percentile. And if you use the QT function to identify those probabilities, that is plus minus negative 2.44. So we have the t value, and this is the probability density function. And if we have t2 function here, then negative, lower to 2.5 percentile has the threshold value of negative 2.446, for maybe 7. And then the upper quantile is the 2.446 or 7. So that can be obtained by this QT function. So actually this point is called 97.5th percentile. So you plug in 0.975 to get this number. And here you can see 2.5th percentile. So you plug in 0.025 to get negative 2.44. So formally, we can say that if t-statistic, absolute value of t-statistic is less than 2.4469, then we reject H naught. And if this is less than 2.4469, we do not reject H naught. So here, H naught is not rejected. So mass PhD's starting salary is not significantly different from all PhDs. Yeah, so this is another graph. So this is our realization, negative 0.94. So it's not really the extreme value. Any questions so far? Okay, so here is just a notation that to conveniently state the theorem. So if we have t distribution, this is almost normal, but t distribution, and if we have area alpha, this point is called the t sub alpha of n. So, okay, so at first, this is the t distribution with degrees of freedom n. This is PDF of t sub n. And this point is called t sub alpha of n. So here, n is just a number. So if the sample size is n, we have to plug in n minus 1. But anyway, so in general, for any natural integer n, natural number n, the t alpha sub n represents this point. Oh, sorry, this point. So this distribution is symmetric. So if you just think about the center and the upper alpha percentile, if you think of alpha quantile, then this point is T sub 1 minus alpha n. Or also you can say that this is maybe the negative T sub alpha of n. Yeah. And also normal distribution, we use the same notation. So for any number. So this does not look normal. But if this is alpha, this area is alpha, then here is Z alpha. Okay.
Is the homework one due on Friday? Like when on Friday is it due? I mean, when on Friday is the homework one?
Homework one is due Friday at night, 11:59. Do you have any other questions?
No.
Okay, thank you. Okay, so yeah. So that's the case. Yeah. So there are several just examples. So this is T sub 0.975 of 6. This is calculated by this and 2.446. And the Z sub 0.975 is equal to just this Q norm of 0.975. That is 1.96 approximately. Remember that in normal distribution, the negative 1.96 to positive 1.96 have 95% coverage. So that means this is 2.5%. This is 2.5%. So this can be written as Z sub 0.025. This is Z sub 0.975. And this is standard normal distribution. This is normal distribution with mean 0, sigma square is equal to 1. Yeah, so to be concrete, the testing procedure is here. So we are doing two-sided test. That means null hypothesis is this, and alternative hypothesis is the both sides of mu naught. So alternative hypothesis just exclude only this point and include the both sides of mu naught. So that's why we said this is two-sided test. And two-sided test, we reject H naught if and only if absolute value of capital T is larger than the T sub 1 minus alpha, T sub 1 minus alpha over 2 n minus 1. So that means here, the alpha is the called significance level, either 1% or 5%. If we take 5%, so basically we take the T sub 0.975. This is 1 minus alpha over 2. If alpha is 0.05, 0.975 of n minus 1. And this is symmetric. So this is negative T sub 0.975 n minus 1. And if the T statistic falls in this range, we reject H naught. So center coverage is 1 minus alpha. So basically it covers 95% of the case. So we reject H naught if T falls in 5% extreme range. If you are more conservative, then you can use the alpha is equal to 0.01. But if everyone changes this number, it's a little arbitrary. So usually we use 5% or 1% for testing. 5% may be the most popular number in many areas. It also depends on the application. So yeah. So if you have to be very conservative, if you are maybe constructing the maybe nuclear power plant or something, then you have to do test with very small alpha to be conservative, to support some hypothesis, to support H1. Yeah, and also it's already 7:45, so we stop here today, and I will give maybe few quizzes on this. Okay, so do you have any questions on homework or lecture? Yeah, and all past exercise questions, the quiz questions have solutions on the website. So you can check it if you would like. Okay, so see you on Tuesday next week. You can remain online if you have more questions. See you.